Welcome back to OwlsPrep. You've worked through topics 1.1, 1.2, and 1.3. Now let's put them together. We'll do a quick recap, then a couple of exam-style problems built to match how the real AP exam actually asks, with context, with units, and asking you to justify. Grab a pencil and pause whenever you'd like to try one before I work it. First, the essentials. Topic 1.1. A function is increasing where bigger inputs give bigger outputs, and decreasing where bigger inputs give smaller outputs. You read that straight from a table. Topic 1.2. The average rate of change over an interval is the change in output divided by the change in input, the slope of the secant line, and in a real problem it carries units, and you can use it to estimate a value. Topic 1.3. A linear function has a constant rate of change, while a quadratic's rates form a linear pattern, changing by the same amount each step. And concavity comes straight from those rates. Increasing rates mean concave up, decreasing mean concave down. And that's exactly how you'll tell whether an estimate is too high or too low. All right, let's practice. Problem 1. The way the exam actually asks. A reservoir is being filled. V of T is the water volume, in thousands of liters, T hours after filling starts. The table gives V at T equals 0, 4, and 8, 20, 44, 60. Part A. Find the average rate of change of V from T equals 0 to 8, with units. Part B. Use it to estimate the volume at T equals 2 hours. Part C. Is your estimate too high or too low, and why? Pause and try all three. Part A. The average rate of change is the change in volume over the change in time, 60 minus 20 over 8. That's 40 over 8, 5,000 liters per hour. Always write the units. Part B. To estimate the volume at T equals 2, start at V of 0, 20, and add the average rate times 2 hours. 20 plus 5 times 2, 30,000 liters. Part C. The move the exam loves. Is 30 too high or too low? Look at the rate on each half. From 0 to 4 the volume rises 6,000 per hour. From 4 to 8, only 4. The rates are decreasing, so V is concave down. Your estimate sits on the straight secant line from the first point to the last. And for a concave down curve, that secant lies below the actual curve. So 30 is an underestimate. The true volume at T equals 2 is a bit more than 30,000 liters. That is what concavity buys you. It tells you which way your estimate is off, without ever computing the true value. Problem 2. A function g is given by this table. At x equals 0 through 4, g is 2, 3, 6, 11, 18. Which type best models g? Linear, quadratic, exponential, or logarithmic? And here's the exam's exact instruction. Justify your answer from the relationship between the change in the output and the change in the input. Pause and try. The input changes by the same amount each step, 1. Now the outputs change by 1, 3, 5, 7, not constant, so it's not linear. But look at how those changes themselves change. Up by 2 every time, a constant amount. Output changing at a constant rate is exactly a quadratic. It's not exponential. That would multiply by a constant factor, and 2 to 3 to 6 doesn't. And it's not logarithmic. Those flatten out, while this speeds up. So, quadratic, justified straight from the table. One quick trap the exam loves. A function k has outputs 10, 4, 0, -2. Falling, so k is decreasing. But its rates are -6, -4, -2. Negative, yes, but increasing. Increasing rates mean concave up. So k is decreasing and concave up at the same time. Falling, but less and less steeply. Decreasing tells you the direction. Concavity tells you how the rate is changing. Never read one off the other. That's the real shape of AP Precalculus 1.1 through 1.3. Not abstract drills, but but problems with context and units, using an average rate to estimate a value, and using concavity to judge whether that estimate is too high or too low, all justified straight from a table. Next up, topic 1.4 extends rates of change to polynomials. If this helped, subscribe, and we'll see you there.